Good day, everyone. I'm Renz Angelo Di Calzada, and my topic for this week for chemistry is all about the colligative properties of non-electrolytes and electrolytes solution. This topic can be found in the Senior High School General Chemistry 2 with the content standard properties of solutions, solubility, and the stoichiometry of reactions in solutions. And the learning competency for this is differentiate the colligative properties of non-electrolytes solutions and of electrolyte solutions. What is colligative properties? When we say colligative properties, these are the physical properties of a solution that depends on the amount of a solute but not on the nature of solute. This means similar amounts of completely different solutes can alter these physical properties in similar quantities. And the colligative properties depend on the ratio of the solute amount and solvent amount. And there is one category of properties that can only be applied to solutions, and these are known as the colligative properties. The properties can be considered colligative only if they are dependent on the amount of solute present in the solution, disregarding the identity of the solute itself. So it matters on the quantity or how many solute is present or is being added on the solvent. There are three major colligative properties. First, we have the vapor pressure lowering. Second, we have the boiling point elevation. And the third one is the freezing point depression. And for a given solute-solvent mass ratio, all colligative properties are inversely proportional to solute molar mass. And we will be discussing more of these colligative properties in the following slides. Let us try to differentiate electrolytes and non-electrolytes. So both these types, electrolytes and non-electrolytes, have colligative properties. Let us describe first what is electrolytes. When we say electrolytes, these are substances that can be formed or can form solutions that are able to conduct electricity through this solution. And such solutions are known as electrolytic solutions. While non-electrolytes are substances that are not capable of forming electrolytic solutions. The key difference between colligative properties of electrolytes and non-electrolytes is that the effect of electrolytes on colligative properties is very high compared to that of the non-electrolytes. Actually, electrolytes and non-electrolytes being a solute, they have the capability to alter the properties of the solvent. However, electrolytes, let's say electrolytes is more powerful in terms of its capability in lowering or elevating such property in the solvent. So let us try, or let us now proceed on our first discussion, which is all about the colligative properties of non-electrolyte solution. So colligative properties of non-electrolytes are the physical properties of non-electrolytic solutions that depend on the amount of solutes, regardless the nature of solutes. So non-electrolytes are substances that do not create conductive solutions when dissolved in a solvent. So for example, sugar is a non-electrolyte because when sugar is dissolved in water, it exists in molecular form, which does not dissociate into ions. And these sugar molecules are incapable of conducting electric currents through the solution. So we need to remember this one. The number of solutes present in a non-electrolytic solution is less compared to an electrolytic solution. Therefore, the effect of non-electrolytes on colligative properties is also very low. So for example, the degree of vapor pressure lowering by adding sodium chloride or NaCl is higher compared to the addition of sugar to a similar solution which is a non-electrolyte. Let us begin with the first property, or let us begin with the first colligative property, which is the vapor pressure of non-electrolyte solution. Vapor pressure is a measure of the tendency of a material to escape into the environment via gas. A substance that evaporates quickly has high vapor pressure and is referred to as a volatile substance. And when a solute is added to a solvent, the vapor pressure decreases. So when we say, I mentioned a while ago volatile, so this time we are going to proceed with the main effect of non-electrolyte solution to the property which is about the vapor pressure. It actually lowers the vapor pressure. So the vapor pressure of a solvent is lowered by the addition of a non-volatile solution to form a non-volatile solute to form a solution. And best example for that is sugar, which is non-volatile, which is under a which is categorized as a non-electrolytic or non-electrolytes. So by definition, a non-volatile substance does not evaporate. So this decrease in vapor pressure can be explained by using the entropy differences of the liquid and the gas phase along with the position of dissolved particles after the addition of the solute. So what is an entropy? So we have three concepts here for entropy. So when molecules transition from the liquid phase to the gas phase, entropy of the system increases. Or let's say when we talk about entropy, this is the disintegration of something. Or it is also synonymous to the term disorder. So the entropy of the gaseous state is greater than the entropy of the liquid state because the gaseous molecules occupy a larger volume. So if the liquid solvent becomes diluted with solute, the entropy of the liquid state increases. So the disintegration of or the energy or the pressure in the liquid increases, and therefore the entropy towards gas decreases. So therefore, even though the gaseous state has a higher entropy, the difference in entropy between the two systems decreases, and the decrease in entropy difference lowers the vapor pressure. That's why non-electrolytic solution or non-electrolytes or non-electrolytic solute can actually lowers the the vapor pressure in that certain solution, especially on the solvent. So let's now talk about the solute particle location. What is its um, function or role in terms of lowering the vapor pressure? So in a pure solvent, all of the liquid molecules on the surface can evaporate and transition to the gaseous phase. In a solution, some spots on the surface are occupied by solute molecules. So there is less space occupied by solvent molecules. Given that, so as an overall, less solvent will transition to the gaseous phase, resulting in a decrease in vapor pressure because of the presence of the solute on top, which occupies the space, and it replaces the solvent molecules there, which lowers, which results in the lowering of the vapor pressure. So now let us now proceed with the equilibrium vapor pressure given by Raoult's law. So if we're going to calculate um, the exact pressure with regards to the vapor pressure, if the addition of solute to the solvent or in that certain solution, if the pressure has really lowered or decreased. So we will be using this Raoult's law. So when we talk about the Raoult's law, it states that the vapor pressure of an ideal solution is dependent on the vapor pressure of the pure solvent and the mole fraction of the component present in the solution. So for an ideal solution, equilibrium vapor pressure is given by Raoult's law, which is P sub A is equal to X sub A times P O sub A, where X sub A is the mole fraction of compound A and PO sub A is the normal vapor pressure of A at that temperature. So note, this is one of those times when you want to make sure you have the vapor pressure of the solvent. So here's the sample exercise calculation of vapor pressure lowering. So here's the problem. Glycerine or C3H8O3 is a non-volatile non-electrolyte with a density of 1.26 grams per milliliter at 25 degrees Celsius. Calculate the vapor pressure at 25 degrees Celsius of a solution made by adding 50 milliliter of glycerine to 500 milliliter of water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr, or which refers to the pressure, and its density is 1 gram per ml or milliliter. So here's the solution. We have to analyze. Our goal is to calculate the vapor pressure of a solution given the volumes of solute and solvent and the density of the solute. So our plan now, we can use the Raoult's law, which is shown a while ago. The equation was shown in the previous slide to calculate the vapor pressure of a solution. The mole fraction of the solvent in the solution, which is X sub A, is the ratio of the number of moles of solvent, which is the water or H2O, to total moles of solution, which is moles of the glycerine C3H8O3 plus moles of water or H2O. Now, let us try to solve. To solve, we need to calculate the mole fraction of water in the solution, and we must determine the number of moles of glycerine and water. So to find the mole of glycerine, so we have moles of glycerine C3H8O3 is equal to 50 ml of glycerine times 1.26 grams of glycerine divided by 1 ml of glycerine times 1 mole of glycerine over 92.1 grams of glycerine, and that yields to 0.684 mole. Now, to find the moles of water or H2O, that is equal to 500 ml water times 1 grams of water over 1 ml of water times 1 mole of H2O over 18 grams of H2O. That yields to 27.8 mole. So this time, we are now going to use the Raoult's law to calculate the vapor pressure of water for the solution. So to calculate the water vapor, that is X sub H2O or water is equal to the mole of water H2O divided by mole of water plus mole of glycerine. So that is equal to 27.8 divided by 27.8 plus 0.684, which is equal to 0.976. Now we will proceed now to the Raoult's law, wherein P sub water is equal to X sub water PO sub water, that is equal to 0.976 times 23.8 torr is equal to 23.2 torr. So that is now the vapor pressure of the solution, 23.2 torr. So the vapor pressure of the solution has been lowered by 0.6 torr relative to that of pure water. So if you notice that the decrease of the vapor pressure is just very low, it's because glycerin is non-electrolytic, or it is a non-electrolytes. Compared to the electrolytes, it could yield to more decrease of vapor pressure. But the thought here is that there is a decrease. It lowers the vapor pressure compared to the normal vapor pressure that is possessed by the pure water. Now let us proceed with the freezing point depression. So freezing point depression is the phenomena that describes why adding a solute to a solvent results in the lowering of the freezing point of the solvent. So when a substance starts to freeze, the molecules slow down due to the decrease in temperature, and the intermolecular forces start to take over, and the molecules will then arrange themselves in a pattern and thus turn into a solid. So when we say freezing point depression, so we expect that the freezing point for this certain solution, given that there is a presence of a non-electrolytes or even an electrolytes, it will go down beyond 0 degrees. So in order to achieve a solid, the solution must be cooled to an even lower temperature. So for example, as a water is cooled to the freezing point, its molecule becomes slower and hydrogen bonds begin to stick more, eventually creating a solid. So that is for an ordinary solvent, which is the water. But in but if it's in a solution, given that the solvent is a water and our solute is the common or the table salt or the common salt, which is the NaCl or sodium chloride. So if salt is added to the water, the sodium ions and chlorine ions attract to the water molecules and interfere with the formation of the large network solid known as ice. Because the 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 molecule, the salt molecule, is being disintegrated to different ions, um, it's one of the reasons that it attracts the water molecules to be close together, which created more bonds, or the hydrogen bonds, which stick more easily or stick more together, which is the reason why there is a depression in terms of the freezing point of that certain solution. So the freezing point depression can also be explained in terms of vapor pressure. So adding solute to a solvent will essentially dilute the solvent molecules, and according to Raoult's law, this leads to a decrease in vapor pressure. So let us try to observe the illustration on this slide. So considering the fact that the vapor pressure of the solid and liquid forms must be the same at freezing point, because otherwise the system would not be at equilibrium. So the lowering of the vapor pressure leads to the lowering of the temperature at which the vapor pressures of the liquid and frozen forms of the solution will be equal. So if you're going to notice on this illustration, that shows the effect of solutes on physical properties. So a triple phase diagram, that is a triple phase diagram that shows the pressure and temperature of the normal boiling and freezing points of a solvent, which is represented by the green lines, and the boiling and freezing points of a solution, which is represented by the purple lines. So notice that at 1 atmospheric pressure, the freezing point has been lowered. That is represented by numbers 2 and 4 in the illustration. So the freezing point depression can be calculated by the formula. The change of final temperature is equal to I times K sub F times the molality. So in this equation, the change of the final temperature is the freezing point depression, and the K sub F is the freezing point depression constant, and I is the Van't Hoff factor. The freezing point depression constant changes depending on the solvent, on the type of solvent that is being used in the solution. And the Van Hoff factor accounts for the number of particles that a dissolving solute creates in a solution. So let's have an example. What is the freezing point of an aqueous solution when enough sodium chloride has been added to create a 0.25 mole solution? The K sub F value for water is 1.858 degrees Celsius per mole. So to solve this, you must remember that sodium chloride breaks into two ions, which is the sodium ion and the chlorine ion, when it dissolves in water. So in simplest terms, this means it has an I factor of 2. So here's the solution. The change of the final temperature is equal to the I times K sub F times the molality. So that is equal to 2 times 1.86 degrees Celsius per mole times 0.25 mole. And that yields to 0.93 degrees Celsius. So this might like the end of the problem, but it is not. The value of 0.93 degrees Celsius is the change in the freezing point. The new freezing point of water, which is normally 0 degrees Celsius, is equal to 0 minus 0.93, which is equal to negative 0.93 degrees Celsius. This time, let us proceed now with the third property, which is the boiling point elevation. The boiling point elevation, or the boiling point of a solvent, will increase when a solute is dissolved in it. This is referred to as boiling point elevation. The elevation of the boiling point is directly independent on the amount of solute present in the solution, but it is not based on the identity of the solute, so it is considered a colligative property. So the relationship between boiling point elevation and vapor pressure can be explained. Yeah, the boiling point elevation can be explained in terms of vapor pressure, and the vapor pressure is defined as the pressure exerted by a vapor in thermodynamic equilibrium with its condensed phases at a given temperature. But in layman's terms, it is simply a measure of the tendency of the solution molecules to escape by entering the gas phase. So a liquid boils when its vapor pressure is equal to the air pressure. So here are some of the concepts of the boiling point elevation. So a solvent's vapor pressure will lower when a solute is added. And this happens because of the displacement of solvent molecules by the solute. So this means that some of the solvent molecules at the surface of the liquid are replaced by the solute, and it can occur in both electrolytic and non-electrolytic solutions. The lower number of solvent molecules at the surface means that fewer will evaporate, and thus the vapor pressure is lowered. For the vapor pressure to equal the atmospheric pressure, at high temperature is required and a higher boiling point is observed. So how are we going to calculate boiling point elevation? The extent of the boiling point elevation can be calculated. It is directly proportional to the molar concentration of the solution. And the amount the boiling point is elevated is determined using the equation. The change of T sub B is equal to I times K sub B times M. In this equation, the change of T sub B is the boiling point elevation, and the K sub B is the boiling point elevation constant, and M is the molality of the solution. The I factor of the equation also factors in any dissociation that the solute may undergo. Since boiling point elevation is a colligative property, the number of ions present in an electrolyte affects the elevation. So here is an example. Let us try to calculate the boiling point of an aqueous solution where enough sodium chloride is added to make a 0.37 molar solution. The K sub B for water is 0.512 degrees Celsius per mole. So here's the formula. The change of T sub B is equal to I times K sub B times M. The change of T sub B is equal to 2 times 0.512 degrees Celsius per or over mole times 0.37 mole. So that is equal to 0.38 degrees Celsius. Water normally boils at 100 degrees Celsius, so the new boiling point of the solution would be 100.38 degrees Celsius, and it is very evident that the boiling point is being elevated by 0.38 degrees Celsius. Time, let us talk more about the colligative properties of electrolyte solution. So actually, the colligative properties of electrolyte solution is just the same with the non-electrolyte solutions. It's just that the power of the electrolyte solution or the electrolyte solute being added to the solvent has been it's more the term that I could associate with that is more severe, or it elevates more, or it decreases even more. So let's try to identify that. So the colligative properties of electrolytes are the physical properties of electrolytic solutions that depend on the amount of solutes regardless the nature of solutes. The solutes present in electrolytic solutions are atoms, molecules, or ions having either lost or gained electrons to become electrically conductive. So when an electrolyte is dissolved in a solvent such as water, the electrolyte separates into ions or any other conductive species. So therefore, dissolving 1 mole of electrolyte always yields 2 or more moles of conductive species. So, the colligative properties of the electrolytes are considerably changing when an electrolyte is dissolved in a solvent. So here's the example. For example, the general equation used in describing freezing point and boiling point changes is as follows. We have here the change of T sub B, which is refers to the boiling point, is equal to K sub B times mole, and the change of T of F, or the freezing point, is equal to K sub F times mole. The change of TB is boiling point elevation, and the change of TF sub F is freezing point depression. The K sub B and K sub F are boiling point elevation constant and freezing point depression constant respectively. And the M, that is the molarity of the solution. So for electrolytic solutions, the above equations are modified as follows. We have here the change of T sub B, or the boiling point elevation, is equal to I times K sub B M, and the change of the freezing point depression, or the T sub F, is equal to I times K sub F times the mole. So I is an ion multiplier known as the Van 't Hoff factor. And this factor is equal to the number of moles of ions given by an electrolyte. Therefore, Van 't Hoff factor can be determined by finding the number of ions released by an electrolyte when it is dissolved in a solvent. So for example, the value of Van 't Hoff factor for sodium chloride is 2, and in calcium chloride is, or calcium dichloride, it is 3. However, the values given for these colligative properties are different from the theoretical predicted values. That is because there can be solute and solvent interactions that reduce the effect of ions on those properties. So the degree of dissociation, which is represented by alpha, of a weak electrolyte can be calculated as follows. So that is alpha is equal to the quantity to the quantity of I minus 1 divided by n minus 1 times 100. So here, n is the maximum number of ions formed per molecule of the weak electrolytes. So in these three major colligative properties in terms of electrolyte solutions, wherein there are electrolytic solute that is being added to the solvent, it is really expected that the vapor pressure, the boiling point, the freezing point, or whatever the non-electrolyte can do to these properties will be even more, it's more exaggerated, I guess, or it will increase or it will decreases more. So for example, in the vapor pressure lowering, it lowers even more, while the boiling point, it elevates more, and for the freezing point, it would decrease compared to what non-electrolyte solutes can do. So what is the difference between colligative properties of electrolytes and non-electrolytes, properties of electrolytes and non-electrolytes? So actually, both these types, electrolytes and non-electrolytes, have colligative properties. But let us try to differentiate the two. Colligative properties of electrolytes versus non-electrolytes. So for colligative properties of electrolytes are the physical properties of electrolytic solutions that depend on the amount of solutes regardless the nature of solutes. While for colligative properties of non-electrolytes are the physical properties as well of non-electrolytic solutions that depend on the amount of solutes regardless the nature of solutes. So the key difference actually between the the key difference between colligative properties of electrolytes and non-electrolytes is that the effect of electrolytes on colligative properties is very high. Yeah, it's very high compared to that of the non-electrolytes. In terms in terms of solutes, here, electrolytes provide more solutes to the solution via dissociation because the ions or the molecular ion will disintegrate to a specific species of ions. We have the anion and the cation, of course. Hence, the colligative properties are considerably changed. But in non-electrolytes, provide low solute to the solution since there is no dissociation. Hence, the colligative properties are not considerably changed. So, konti lang. Although there is still a change, but very minimal lang. So, in terms of effect on colligative properties, in electrolytes, the effect of electrolytes on colligative properties is very high. It is really very high compared to non-electrolytes. But the effect of non-electrolytes on colligative properties is very low compared to electrolytes. So here's the summary. Colligative properties are physical properties of solutions that do not depend on the nature of a solute but the amount of solutes. And the difference between colligative properties of electrolytes and non-electrolytes is that the effect of electrolytes on colligative properties is very high compared to non-electrolytes. So that would be all my topic for this week. Thank you so much for listening. And here are my references. Thank you so much.